In this video, we're going to talk about linear combinations. If a vector v in vector space V can be written in the form v equals c sub 1 times u sub 1 plus c sub 2 times u sub 2, and so on up to the nth term, where c sub 1, c sub 2 through c sub n are scalars, then we say our vector v is a linear combination of u sub 1, u sub 2 up to the nth term, where c sub 1, c sub 2 through c sub n are scalars. Let's take a look at this question. Can the vector u be written as a linear combination of the vectors in S, where u is equal to 1, negative 8, 12, and S is equal to vectors 2, negative 1, 3, and 5, 0, 4. If we think back to our definition of a linear combination, the definition tells us, essentially, that if we can find two constants, c sub 1 and c sub 2, so that the following statement is true, then it's a linear combination, or it can be written as a linear combination. So our vector equal to c sub 1, a scalar, times our vector 2, negative 1, 3, plus our scalar c sub 2, times 5, 0, 4. Again, if we can find constants c sub 1 and c sub 2 that will make this statement true, then the vector u can be written as a linear combination of the vectors in S. So let's try it. First, I'm going to distribute c sub 1 and c sub 2 throughout the respective vectors. Here's vector u on the left. And distributing c sub 1, I get 2c sub 1, then I get negative 1 c sub 1, positive 3 c sub 1, plus, and if we distribute c sub 2, we get 5 c sub 2, then we get 0, then we get 4 c sub 2. Now, we use vector addition, and we set each sum equal to the corresponding entry in vector u. So in other words, we have 2c sub 1 plus 5c sub 2 is equal to 1. Then we have negative c sub 1 plus 0 equal to negative 8. Then we have 3c sub 1 plus 4c sub 2 equal to 12. Now clearly it's easiest to solve for c sub 1. We have negative c sub 1 is equal to negative 8. And we can apply the cancellation property, which basically eliminates our negatives on each side. So we know that c sub 1 is equal to 8. Now if c sub 1 is equal to 8, we can solve for c sub 2 by plugging in 8 for c sub 1 and solving for c sub 2 in either of the two equations that contain c sub 2. I'll use the one on the top. So I have 2 times 8 plus 5c2 is equal to 1. This is 16 plus 5c sub 2 is equal to 1. Subtract 16 on both sides. So we end up with 5c sub 2 is equal to negative 15. Or in other words, c sub 2 is equal to negative 3. By obtaining these values for c sub 1 and c sub 2, we are now able to show that we can write vector u as a linear combination of the vectors in S. So in other words, we can say that u is equal to 8 times 2, 1, negative 1, 3, minus 3 times 5, 0, 4. So this concludes our example. I'd also like to mention briefly that if solutions cannot be obtained for c sub 1 and c sub 2, then vector u would not be able to be written as a linear combination of the vectors in S. Anyway, that's it for today. I hope you found it helpful, and we'll see you next time.